Akshay? Or
Yeah,
running
that's
on
fine.
Berkeley time or normal time?
I don't know. We can wait. That's cool.
Like, of all the devices I have, the only one that has a microphone that works is the super tiny tablet.
Cool. You can see my laser pointer, right?
Yep.
That's pretty cool. Oh, how do I get rid of it?
It's stuck there forever.
Okay.
Wow, this is a really unflattering angle. Okay, I guess the number of panelists is, or the number of attendees is kind of, participants is kind of stabilized. So you want to get started? Okay. I'll
Yeah,
introduce
sure.
you. Okay,
Yeah,
well, thank you everyone for joining the last day of the Mathematics of Online Decision-Making workshop. And we'd like to start off today by inviting our very own Akshay. And he is a principal researcher at Microsoft New York and has a lot of really exciting results in bandits, and has now have recently many very exciting results in reinforcement learning. So I'm very excited, and please take it away.
Thanks, Alan, and thanks everyone for coming, and West Coasters for waking up kind of early. I guess this is the MSR New York City day of the workshop, so I'll just like kick things off. Yeah, so this is going to be a talk about representation learning and exploration. And there's kind of like two stories around like why you might be excited in this problem. The first one is like how I got excited in this problem. And the second one is maybe more why other people might be excited in this problem. And I kind of want to tell you the first one. It's going to be a little bit of like, you know, like a bit of like, I don't know how you say it, like a spotlight of some previous work we've done. And then it'll have like a broader theme with what's going on in the main course. Okay, so back in 2015, I had just finished my PhD and I joined MSR New York, and John Langford, Alec Agarwal, and I decided we wanted to start learning about reinforcement learning. And we read a bunch of stuff. I had not worked on it before. And we started trying to understand if we could develop provably efficient reinforcement learning algorithms that scale to like the complex kinds of domains that you might see in robotics and gaming and dialogue. And so what we were really trying to do is use nonlinear function approximation and address exploration at the same time. And like, you know, we like thought about this problem for a while, and I think this is like the first whiteboard picture I have from some of our discussions. And over time, we slowly started developing some understanding of what is going on statistically in some of these problems. This is also with folks like Nan Zhang and Rob Shapiri and Wen Sun. And then we started thinking about maybe an intuitive model called the block MDP, where we're able to develop some algorithmic results. So I just want to tell you a little bit about one of these. But first, let me tell you what the block MDP model is. So it's a latent state model in which the agent, there's like a discrete latent state space that governs the dynamics of the world. So you can think of this like a tabular problem, but the agent does not see the tabular state. Instead, the agent is going to see some high dimensional observation produced by some emission distribution associated with each latent state. So the story is that, you know, maybe we're considering like a navigation task, and the agent is in a latent state, which is just its XY position, something very, very simple. But the agent doesn't see the XY position. The agent has a camera on its head and sees like a image, you know, of its surroundings. And based on its image, we'll take an action. And based on the latent state, the position of the action, the system will transition to a new latent state, and so it's going to go on. So this is the kind of dynamics model that we're thinking about. And the point is that the agent operates on, you know, these rich observations, which could be like, you know, extremely complicated. And so you really have to use nonlinear function approximation here, right? We have to use a convolutional neural net to deal with images, or so you know, something complicated has to go on here. But you know, if you think about this, you know, for 30 seconds, you'll say, oh, this is a POMDP, and I don't want you to consider it as a POMDP. So what I'm going to assume is that the latent states are going to be decodable from the observations, which means that each latent state is associated with an emission distribution over observations. And these distinct distributions, one per latent state, actually have disjoint support. And so really this is a Markov decision process on the observation space, but the observation space is very complicated. Okay, so there's not going to be any partial observability, and this is, I don't know, we haven't really thought about how to relax this. It would be awesome if we could. This is just going to make our lives a little bit easier. So this is the model we've been thinking about, and we've been able to develop some algorithms with some reasonable guarantees. I'm just going to tell you just briefly about one. So this is this algorithm called Homer, which is joint work with Dipendra Misra, Michael Hanoff, and John Langford. And the algorithm is going to interleave 2 steps. So one is like exploration. So it's going to use some policies to collect some new data. And the other one is sort of a decoding step to try to discover what this latent state space looks like. And the decoding is via reduction to supervised learning, which is how we can leverage like nonlinear function approximation methods. And what the algorithm does is it uses like a contrastive learning kind of objective, where it tries to train a binary classifier to figure out if transitions like XA, X prime triples are from the real world, like real transitions that could have occurred in the environment, or fake transitions that our algorithm is splicing together just to create negative samples. And so somehow this contrastive objective is able to discover some notion of a tabular state space in your problem. And that's going to allow us to use tabular methods to explore. And that's basically all I want to tell you about the algorithm. I'll tell you what we prove. So we're going to, this process is decodable. So we're going to assume that we have a class of functions, this capital phi, that contains the true decoder, the true mapping from the observation space to the latent state space. And we're going to also assume that this class capital phi doesn't have like doesn't have unbounded statistical complexity. And we're also going to assume that there is some way to hit every latent state with reasonable probability. So for every latent state, there exists some policy that gets there with probability, at least eta. And yeah, with Dipendra, Michael, and John, we're able to show that this algorithm Homer can find a near optimal policy for this problem and to cover the state space in a number of samples that scales polynomially with the number of latent states, the number of actions, the time horizon, 1 over this reachability parameter, 1 over the accuracy parameter, and the log cardinality of the function class. And I guess one thing I want to mention here is that this log cardinality of function class is coming just from like a very standard supervised learning analysis. So you could replace this with metric entropy or other statistical notions. And this is sort of what I mean when I say I want to be able to accommodate nonlinear function approximation. Any function class for which you expect supervised learning to work, we should be able to use in reinforcement learning. And on the computational side, this algorithm, we can show it runs in polynomial time, assuming we can solve certain supervised learning problems. So this is really like a reduction style of algorithm where, I don't really know if I can train a neural net to convergence, but if I assume I can do that, I can, solve this block MDP. And so there's this computational assumption that we're making, and we need to sort of verify if this actually makes any sense. So we did implement this algorithm, and we ran it on like a very hard combination lock type problem where there's like 100 time steps, and at every time step there are 3 latent states, 2 are good, 1 are bad. And from the 2 good latent states, there's 1 action which will advance you down the good chain, and 9 actions that will advance you to the bad chain. And from the bad chain, you're stuck, and you have to stay in the good chain to get any reward. So if you take random actions in this problem, it will take you 10 to the 100 episodes to hit the reward, and obviously we cannot run for that long. So we're trying to do something that something non-trivial. And also there's some emission distribution, which like I'm not going to get into. And we ran a bunch of baselines, like standard PPO. It doesn't really have a very good exploration strategy, so it's unsurprising that it fails. We also ran this random network distillation exploration bonus that people use empirically, and this works kind of well, but it has somewhat high variance. So at some stage, like it fails to do something, and then it fails afterwards. And then we ran Homer, which is somehow like quite stable, is able to discover the right state space and explore all the time steps. So I'm just showing you the coverage of these algorithms. So that's like sort of flavor of a kind of thing that we're able to do in the block MDP land. And stepping back a bit, the block MDP, I kind of like this model because like conceptually what we're doing is we're saying, here's this tabular problem. We know how to solve tabular MDPs for the most part, but I'm going to associate, I'm going to attach like a complex observation process with a hidden tabular structure. So I'm like going to decouple the dynamics of the world, which are relatively simple, from an observation process, which can be fairly complicated. And that's like a cool, I think that's like a cool way to think about how to develop new algorithms for reinforcement learning that have to use nonlinear function approximation. So the block MDP, yeah, we have to use nonlinear function approximation here. So that's like, it's good. It forces us to do something hard. Perhaps it's a good model for real settings like navigation. And we have been able to develop some algorithms that show that it's statistically and algorithmically tractable. On the other hand, when you start playing with these algorithms in practice, you start to get annoyed by the fact that the latent space is discrete, because somewhere in your algorithm, you have to do some discretization. And this is not very gradient friendly. So it's like actually not that compatible with deep learning. So that's something that like I found to be a bit annoying. And maybe a more minor point is like, there's no reason to believe that decodability is actually required as long as you can approximate the value functions and policies from your observations. So that's like maybe something we'd like to remove. Okay, so that's like how I got to this problem that I haven't told you about yet. The other way you might arrive at this problem is by just seeing what the RL theory community has done in the last 2 years, which is like study this linear function approximation stuff like super intensely. And of course, this is not like a new thing, linear function approximation reinforcement learning. We have all these classical results. But in the last 2 years, there's just been like I don't know, like a flood of activity in this area. And I'm actually highlighting all the ones that were presented in the RL theory seminar. So if you're paying attention to RL theory land, you must know about some of this stuff. And I think this stuff is like super cool. And I'm like learning so much by reading these papers. But then we started asking, so in these papers, what are they doing? They're going to use like they're going to use linear functions of some given feature map to approximate the value functions and policies and things like that. And we started asking like, where do these features come from? So a very natural question is, can we do something to learn the features so that we can apply these linear RL methods that we've just developed in the last couple of years? And so that's what this talk is about. We're going to do provably efficient feature learning or representation learning in perhaps the simplest model in which we know linear function approximation can work, which is the low rank MDP. And so if you're a block MDP enthusiast, you can think about this as how to do nonlinear function approximation beyond this block model. And if you're a linear RL enthusiast, you can think about how to learn the features so that we can do linear RL stuff afterwards. And yeah, the key challenge is that learning these features and exploration are intertwined. And this is a bit complicated because you can't use techniques like optimism in the same way, because when you're doing nonlinear function approximation, your function class does not support the confidence intervals that you might get from linear or tabular function classes. So this is going to be the key challenge. Maybe now is a good time to stop if there are any quick questions. Okay, sweet. So I know I haven't said anything technical. I will tell you something now. Okay, so what is this model? This is the low rank MDP. It has many names. I like low rank MDP, but there's this factorized linear MDP, all sorts of things. Basically, the dynamics, which is this like transition matrix T, factorize into two terms. One is this feature map phi of XA, and another is this embedding mu of X prime. And the embedding dimension, which is the dimensionality of the feature map phi and the feature map mu, is D, which is going to be much, much smaller than the size of the state space or the observation space. And we're going to actually think about, so this is like some structural assumption about the way the world works, right? And we're going to think about the setting where you don't know this feature map phi. But maybe like I'll tell you a couple structural things. So first of all, the block MDP is a low rank MDP. So if you have a block MDP, you can write it as a low rank MDP where in addition to this low rank factorization, the right-hand factor, this mu matrix, has to be block diagonal after permutation. And this is just so that each observation can only be generated by one of these latent ranks or factors or states. So the rank of the matrix is the number of states in this problem. But of course, this is a very, very strong additional assumption beyond low rank. So you can create these problems. It's like basically generic to create a problem where the transition operator is low rank, but does not emit any non-trivial block factorization. And another structural connection is this stochastic factorization that comes from this paper by Andre, Barreto, and Doina and Joel, where you assume that both the phi matrix and the mu matrix are row stochastic. So the features live on the simplex and the rows of the mu matrix live on the simplex. And this has a really nice interpretation in terms of sampling, in terms of some latent variable model. So I'm at some state, I'm about to apply an action. The way I'm going to transition is I'm first going to sample a latent variable z from this distribution phi of xa. And then I'm going to sample the next state from an emission distribution associated with the latent variable z. So this is kind of like very close to the block MDP, except that the latent variables or the latent states are not decodable. On the other hand, it's not an HMM because you don't have to remember the history to figure out what the distribution over the next latent variable is going to be. So this is this model studied by Barreto, Prekop, and Pinot. And they show that you can like swap the factors and get very efficient algorithms. And it's also an example that was mentioned in this paper by Jin, Yang, Wang, and Jordan. So that's just some like structural stuff that, this is kind of a tangent. Getting back to the problem at hand, we should maybe ask, why should we study these low rank MDPs? And the first point, which I think probably all of you know, is that this problem is tractable if the feature map is known. This is this really nice result by Jin, Yang, Wang, and Jordan. They give this algorithm, optimistic least squares value iteration, that gets a square root t type regret when the feature map is known. Something that I guess we kind of knew before is that actually this problem is statistically tractable even if the feature map is not known. So this low rank MDP model has Bellman rank D. Bellman rank is this concept that we came up with in this paper, no matter what the function class you're using is. And you can, if you have a function class of candidate embeddings that contain the true one, then this algorithm Olive has a sample complexity that scales like what I'm showing here. And again, this has this log cardinality of phi dependence over here, which is sort of what you would hope for. This is sort of allowing you to scale to nonlinear function approximation. On the other hand, Olive is not computationally efficient. So the goal for this project is to get a computationally efficient algorithm with a similar guarantee to Olive. And that's kind of what we do. That's basically what we do. There's only one caveat, which is this thing here. So we're going to make a slightly stronger realizability assumption. So we're going to assume that you have a function class capital phi that contains the true feature map phi. We're also going to assume you have a function class capital upsilon that contains the other factor mu. So this is going to be like a model-based realizability. You have the full transition operator in your function class, but this is a relatively weak inductive bias. Right? These things could be quite large function classes. And we're also going to work in an Oracle computational model, just like in the Homer setting. And we're going to assume you can optimize and sample from these things. So when you take a phi and a mu, you get a transition operator, and you should be able to sample from it. That's what we're saying here. And so what we proved, this is joint work with Alec Agarwal, Sham Kakade, and Wen Sun. We have this algorithm, it's called Flambe. It stands for feature learning and model-based exploration. And we show that this algorithm can learn a low rank MDP. So it has its own feature maps, phi hat and mu hat, that gives you this kind of system identification guarantee. So it's going to actually universally approximate the dynamics of the true world for any roll-in policy and any time step. So this is, you pick any roll-in policy you like, you pick any time step, you apply actions by following that policy pi, and you get to some state xh, and then you look at what your model is going to predict about the next state and what the true transition operator predicts about the next state, and you measure the total variation distance. And we're going to get this to accuracy epsilon for any policy and any time step. And this is going to be good enough to optimize any reward. Okay, and we can do this in a sample complexity that scales polynomially in D, the number of actions, the time horizon, the accuracy parameter, and the statistical complexity of the function classes. Again, this is like almost a standard generalization argument. So you can scale this to nonlinear function classes with bounded metric entropy or stuff like that. And maybe a technical point is actually we've been able to relax the reachability restriction that we had in the Homer setting. And okay, and the algorithm runs in polynomial time in this Oracle model, assuming you can optimize and sample from these functions that you have. Let me just tell you some other random facts. So we actually do have a formal representation learning guarantee. So we're going to learn a low rank MDP M hat, which has features phi hat. And in this model, for any reward, the optimal policy and Q function will be linear in our features, which means due to the total variation guarantee that in the true world, a near optimal policy is going to be linear in the learned features. So this is like you've actually learned a representation phi hat that allows you to approximate all the things you might care about in your true world. We're also, because we have a model, we're able to do reward-free learning, kind of like what Emily talked about on Wednesday. So you can optimize any reward function that's given to you like you get programmatic access to the reward function. You can optimize any such function with no further experience from the environment. And we also have a version where you don't have to sample from the model, so you can do some sort of like real world planning, but it requires some slightly stronger assumptions. Okay, so I want to tell you a little bit about the algorithm, and we'll see how much of the proof we can get to. Okay, so the algorithm, actually conceptually, I think it's quite simple. So you're just going to start with a random policy, and you're going to just repeat this thing for many iterations. And in each iteration, you're going to use the previous policy that you have to collect some data. So you're going to roll, this policy is going to recommend actions on the basis of states. You're going to follow the first H recommendations according to the policy, and then you're going to take the H step random, and you're just going to terminate the episode however you like. And what you're hoping for is that this policy sort of covers the state space at time H, so that you can learn the model accurately, uniformly at time H. But there's a technical point, is that we don't even know how to measure coverage. But that's like sort of intuitively what you're hoping for. And then you're going to just learn the dynamics using the data that you just collected, or using all the data that you have. And then maybe the hard part is you have to compute a new exploratory policy that hopefully gets you to some new place. And so maybe the picture, this is sort of not exactly the right picture, but maybe it's helpful, is you want row j-1 to cover the state space at time h. So now when you take a random action, you'll be able to uniformly approximate the dynamics from time step h to h+1. And actually, you'll have like decent coverage at time step h+1 up to a factor of the number of actions a. And what you'd like to do in this, when you compute an exploratory policy, is to sort of shave off this factor of a again. So you'd like to say somehow row j does not take the h action randomly, but just gets us directly to time step h+1 without paying this uniform random action. So that's sort of what you're sort of trying to like boost this coverage probability as you go forward. Okay, and there's sort of two questions we have to ask. So one is, how do you learn the dynamics? And the other one is how to compute the exploratory policy. So learning that the dynamics, I think, is actually kind of cool. This is not something I just learned. This is some like classical result. This is like very classical in statistics world. So here's sort of what we're going to do. You're going to collect these triples, xh, ah, xh+1. And you're just going to solve the maximum likelihood problem. So you're just going to search over your function classes for the pair that maximizes the log probability of the data. And something that was actually quite surprising to me is that this actually works. So this is like very classical, but here's a version from Tong Zhang. So if you assume realizability of the dynamics, you can actually guarantee that when you solve the MLE problem, you can accurately approximate the transition operator in total variation on the data distribution with which you collected transitions. Okay, and the right-hand side here is like what you might expect from a standard generalization argument, although this is not a standard generalization argument. There is something clever going on here. Okay, so let's call this thing the error. This is the pointwise error of the transition operator when you are at state xh and you apply action ah. Okay, so you can also prove a martingale version that's like just kind of technical. And now, okay, so what I want to do is I sort of want to say that these exploratory policies, so I've written this for all the exploratory policies I've seen so far, I somehow want to be able to track if these exploratory policies are covering my state space. And so this is sort of where like where we're going to use the low rank MDP property in a very strong way. And I guess the point is that there's a lot of magic happening inside this expectation. So how did you get to xh-ah? Well, you got to xh-1, ah-1, and then you applied a transition. But the transition is low rank. And so you should actually be able to write this expectation in terms of the feature at the previous time. And now you're going to detect some d-dimensional quantity in which you can measure progress. So this is basically what we do. That's sort of like maybe the key idea. Okay, so I'm going to define these covariances of my exploratory policies. So this is if I were to roll in with my exploratory policy and look at the true feature at time step h. And this is the covariance of the true feature. Basically rewriting this martingale inequality, I can get something that looks like this. And so this is the error. This is like when I wrote this as an expectation one step backwards, this is the feature at the previous time. So now I'm writing this in terms of like a d-dimensional Euclidean norm. Okay, and this is, so now it's kind of clear what you want to do. You sort of want to make sure that your exploratory policies have a very large, covariance matrix at the previous time. And if that's the case, you'll be able to transfer it to any other policy. So that's maybe the key idea. And so yeah, this is the basic property. For any function f and any policy pi, the expectation of f of xh, when you roll in with policy pi, it can be written as a d-dimensional inner product in the true feature, where the first term depends on pi, and the second term actually does not. It just depends on f. And so this is basically what we're going to do here. Okay, so I think I'm going to skip the next slide because it's perhaps the most technical one. Yeah, so basically what we do is we want to sort of maximize this. We want our policy rho to sort of have good quadratic form so that you're gaining in the coverage. The issue is that you don't actually know the features. So what you do is you ask your exploratory policy to have good coverage in your learned features at one time step even before, and then this will ensure that you have good coverage in the true features at the current time. So that's sort of I'm going to skip all this stuff. Okay, so that's the basic idea. So you can use the feature map at the previous time to measure your coverage, and you can use your learned feature map one time step even before as a potential function for you to find an exploratory policy. And so what you can say is somehow if maybe I should skip this. Okay, so that's like sort of how the proof goes. I think the one key idea is somehow, even though you don't have the feature map, it does exist a potential function, which is the feature map at the previous time. And so now you can use this thing to track your progress and measure coverage and all these things. So I want to like return to this conceptual point, which is about like how are we like able to do nonlinear function approximation in some sense. And basically what we're doing is we're taking models that we know to be tractable and attaching a high dimensional observation space. And so we've done this in the block MDP, where the model that we know to be tractable is the tabular one. We've also done this in the low rank MDP, where the model that we know to be tractable is the linear MDP. And so we're able to get some results where you don't know this latent state, but you can decode it. We're able to get some results where you don't know the representation, but you can decode it. And there's still a bunch of other stuff that we actually don't know. So there's a bunch of other settings that we know to be statistically tractable, but computationally intractable. And I feel like this is like maybe a general recipe for us to discover new algorithmic principles. So you take your favorite MDP problem or your RL problem that you know to be tractable, you attach this like rich observation space, and you force yourself to use nonlinear function approximation, and hopefully you can develop a new algorithm that can solve that problem. There's a bunch of open questions here. I feel like this is like just sort of maybe cracking the surface. You might ask about the dependence on the number of actions, because in the linear MDP setting, you actually don't need to depend on this. But this problem is kind of like, it's kind of like a sparse bandit problem where you should have to depend on the number of actions, because there's like this feature selection component, which really looks like running the lasso or something like that. Sharp rates and regret, yeah, we have no idea. Our bound is pretty bad, but it is polynomial. And does it actually work? Well, the jury's out, but we are trying it out. So I'll just end with some links to the papers and thank everyone. That's from left to right: Alec, Michael, Sham, John, Dipendra, and Wen. Thanks a lot.
Thank you, Akshay. While we're still really good timing, we have a couple more minutes. Are there any questions? While maybe Alex, you can get set up if you don't mind.
Oh, there's a question. Oh, go on.
Go ahead.
Oh, there's one question in the chat, in the Q&A. Is the feature function aims to truncate or concentrate the large state space? Yeah, that's kind of right. So the state space is going to be really complicated, but somehow all of the transition dynamics are passing through this d-dimensional bottleneck. So you can sort of ignore all this spurious information about the state, except for the fact that except for these d bits or d reals. And that's gonna sort of, it's like a compression operator.
Hi.
Could you unshare, please?
Oh yeah, sorry.
Thanks.
Any last questions? Remember that we'll have a discussion section in an hour. Our discussion session.
I can ask it then. Thank you.
Okay. Well, thank you again, Akshay. And our next speaker is Alex Lipkins, also